A team led by Carnegie's Thomas Shiell and Timothy Strobel developed a new method for synthesizing a novel crystalline form of silicon with a hexagonal structure that could potentially be used to create next-generation electronic and energy devices with enhanced properties that exceed those of the. Their work is published in Physical Review Letters. Silicon plays an outsized role in human life. It is the second most abundant element in the Earth's crust. When mixed with other elements, it is essential for many construction and infrastructure projects. And in pure elemental form, it is crucial enough to computing that the long-standing technological hub of the U.S., California's Silicon Valley, was nicknamed in honor of it. Like all elements, silicon can take different crystalline forms, called allotropes, in the same way that soft graphite and superhard diamond are both forms of carbon. The form of silicon most commonly used in electronic devices, including computers and solar panels, has the same structure as diamond. Despite its ubiquity, this form of silicon is not actually fully optimized for next-generation applications, including high-performance transistors and some photovoltaic devices. While many different silicon allotropes with enhanced physical properties are theoretically possible, only a handful exist in practice given the lack of known synthetic pathways that are currently accessible. Strobel's lab had previously developed a revolutionary new form of silicon, called C24, which has an open framework composed of a series of one-dimensional channels. In this new work, Shiell and Strobel led a team that used C24 as the starting point in a multi-stage synthesis pathway that resulted in highly oriented crystals in a form called 4H silicon, named for its 4 repeating layers in a hexagonal structure. Interest in hexagonal silicon dates back to the 1960s, because of the possibility of tunable electronic properties, which could enhance performance beyond the cubic form, Strobel explained. Hexagonal forms of silicon have been synthesized previously, but only through the deposition of thin films or as nanocrystals that coexist with disordered material. The newly demonstrated C24 pathway produces the first high-quality, bulk crystals that serve as the basis for future research activities. Using the advanced computing tool called PALLAS, which was previously developed by members of the team to predict structural transition pathways—like how water becomes steam when heated or ice when frozen—the group was able to understand the transition mechanism from C24 to 4HC, and the S. In addition to expanding our fundamental control over the synthesis of novel structures, the discovery of bulk 4H silicon crystals opens the door to exciting future research prospects for tuning the optical and electronic properties through strain engineering and elemental substitution. Shiell S. We could potentially use this method to create seed crystals to grow large volumes of the 4H structure with properties that potentially exceed those of diamond silicon. Story source. Materials provided by Carnegie Institution for Science. Note: content may be edited for style and length. Thanks for watching. Please subscribe my channel for more updates.